All right, so we're looking at lesson set 43 still, get a full screen. I'm gonna do problems 64 to 80, 89. All right, and a bit of commentary on this. We're getting into some of the newer material. So we're gonna have to really chat a little bit about some of these problems. And the ones that we see that are familiar, hopefully we can do them quickly and easily, kind of like flashcards. All right, so powers and roots. I should have done this in the last video. It was attached to the ln of 20 question, which we found was about 3. So I'm not quite sure how to talk about this because 3 is 3 divided by 1, and I'm not sure how to talk about a first degree root. So I guess that's an interesting moment. The root of a line, of a one-dimensional picture. I don't know. Anyway, then I put in a mixture problem from Algebra 1. Just to at least acknowledge that we probably should be doing a couple of word problems. It's just that they take a lot of time. As an instructor, I feel like it's more important that you learn e to the x and ln of x and trig and unit circles. So I put it on the back burner, but let's just do at least one for your SATs. So you got a batch of candy that you want to sell for 70 cents. You want to sell 50 pounds of candy for 70 cents, but it's coming from 2 batches, one 50-cent candy and one 80-cent candy. All right, so how do we approach that? Slow the brain down a little bit. Got 2 batches, one at 50 pounds, the final batch 50 pounds. So how much at 50 cents? Well, what if I said 5 pounds at 50 cents? Well, how much at 80 cents? I hope you'd say 45. Okay? I mean, the total amount of pounds is going to be 50. And what if we increase that to 10 pounds at 50 cents? Well, I think we got 40 pounds at 80 cents. And how about 15 pounds at 50 cents? Well, 35 pounds at 80 cents. How about X pounds? I guess you got to slow your brain down. Figure out what's over there. So pause it, pause the video, think about that. If you're not sure, I'm just going to keep talking. Well, I think it's 50 minus X. I mean, here's a marker with a cap on it. The length of the marker, you can see the length of the marker. Well, what if I take the cap off? Isn't it that length minus C, the cap? And that's what's left? Well, that's what you got to think about. So what's the equation for this? We know we want to finish with 50 pounds at 70 cents. So why don't I put the 70 cents here? All right, so what's it coming from? Coming from one batch at I wish I didn't have the same numbers here, but that's what I put. So this is 50 cents at what? At X amount. And then I guess we got to add to it the 80 cents at what did I say? 50 minus X. So my first time talking through that, right? If I did another 5 or 6 problems on 5 or 6 lesson sets, maybe I'll explain it better. Let's move right along here. So trying to give you an entry-level calculus problem based on Algebra 1. So I'm looking at X squared. Here's X squared. X times X. And if I add a sleeve to that area, if I slide a sleeve on, I just made that area a little better. If I slide that on, and that dx I'm representing as 0.001 right there. Could have been a whole lot more. 0.001, 1, 2, 3, 4, 5, 6. I could get even closer to 9. 9.1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You divide that by that, and you're going up at 6 to 1. And we've done more table values, lots of table values in previous lesson sets. And so I'm hoping that you recognize that X squared changes at any instant by doubling the X value you're at. So at 0, doubling 0 is 0, doubling 1, I'm going up at 2 to 1. Doubling 2, I'm going up at 4 to 1. Doubling 3, I'm going up 6 to 1. At -1, I'm going down at 2 to 1. And I hope you start to see a little slope field emerge. That's what we call it when you get to that level of study, to get a feeling for how this is changing. Now, if I multiply that by 4, I'm going to get 8x minus 10 as a what? As a formula for talking about how at any instant, how I'm changing. Put 0 in. Oh, what a coincidence. I'm going down at 10 to 1. Oh, so at 0, I'm at 7. And I'm going down at 10 to 1. Well, what happens when I get to that moment there? Well, it looks like that's 10 over 8, which is 5 over 4. Sure seems like this x value is 5 over 4, and that's when my slope is 0. And what did I ask? I asked for the rates of change at the y-intercept. I know that one now. And I know the rate of change at 5/4, which is minus b over 2a, by the way. Right, just matching up with what we've done before. Well, that's where my slope is 0, so that's where I get that k value, hk, that minimum value. And how do I find that? Well, of course, I plug 5/4 in to find it, but I didn't ask that. I just asked for what's the rate of change at the vertex? 0. And that's the x value at the vertex. I'm not even sure I asked that. What's the rate of change at the y-intercept? It's given. But for any polynomial, I don't care, you throw x cubed in here, so on and so forth. Right? When I put a 0 in, everything with a variable is disappearing except for that constant rate. That makes graphing a whole lot easier, knowing the rate of change of the y-intercept and knowing what the y-intercept is for polynomials. It's a nice tool, something nice to know. So to this point in time, we spent a lot of time finding roots. Well, now we're going to need those roots. And what are those roots? Well, I'll just find them. 0 is a root. 4 is a root. 2 is a root. And notice I put a dot here. Oh, well, that's an even exponent. These get dashes. They're odd. I know something's going to happen. X minus 4. The graph of x minus 4 looks like that. I get a sign change at 4 from negative to positive. 3x minus 6 cubed. Not quite sure what that looks like, but I know one thing. Cuts through at 2. Whoops. Again, sign change. 2x squared. I know what that looks like at 0. No sign change. And this is a product. If I have a positive times a positive times a positive, I think I'm greater than or equal to 0. I think that's true. If one of these changes signs, is that greater than or equal to 0? If I multiply a positive times a negative, I think that's false. I got a sign change. Now, sometimes you get a sign change, like here, when x is 5 or 3, I'm going to get a sign change there. When it's 5, that parenthesis is positive. When it's 3, that parenthesis is negative. Do 5 and 3 affect this at all? Putting 5 in, putting 3 in. No, I think that's not changing this parentheses. Putting a 5 in over here, that's positive. Putting a 3 over here, that's positive. Putting a 5 here, positive. Putting a 3 here, positive. Putting a 5 here, positive. Putting a 3 here, negative. That's the conversation you need to hear. Now, maybe your brain needs to hear it more than once. But once I find one answer, true or false, then I know if it's true, then that's going to be false. That's going to be true. That's going to stay true because there's no sign change here. If it was false, then I know that's going to be true because there's a sign change. I know this is going to be false because there's a sign change. I know that's going to stay false because there's no sign change. That's what you're going to try to learn. And I'm going to learn to get an eraser, put it in my pocket when I start these videos. Then I wouldn't have to waste your time by walking over there and coming back here. All right, so all I got to do is find out. If I put a number bigger than 4 in, like 1,000,000 or 5, your choice, I know that's positive. I know that's positive, and I know that's positive. And a positive is greater than or equal to 0. So that's true. You're going to find that's false, that's true, and that's true. And then hopefully you're going to learn how to write negative infinity to 2, because 0 also works. Said equals 0, so that's one section that works. 2 to 4 doesn't work, but I pick up again at 4 and 4 works to infinity. Now, I think it's more important to learn how to sketch these in a calculus class. I think it's easier to look at a graph and answer questions like, if this was an acceleration function, where's grandma accelerating? When is she accelerating? When is she on Route 91 starting to speed up? I really want to know how fast she's going, but that's another topic. Well, no, let's just graph this now. So add 4, add 2, add 0. All right, I have a polynomial, and I know that polynomials like x squared, y equals x, and y equals x squared, and so on and so forth. Right? I know the end behavior is going up. All right, and I have a linear root, then I have a cubic root, then I have a quadratic root. Now, I don't know what these local maxes and mins are. That's what calculus is for, but I do know the shape of the graph. And so can I look here and say, when am I bigger than or equal to 0? Well, I hope you can match it up. Each of these x values is producing y values above the x-axis, right? Here's the x-axis, right? And then these don't. No, these don't. That's below. But then we pick up again. And I hope you can see those values expressed symbolically here. Okay, so we got a conversation started. We'll keep doing those problems, keep talking about them in class, and hopefully, when all is said and done, it's like a flashcard. All right, so domain. Well, domain is all about what can I use? What inputs are permissible? Right, those are x values. So we're talking about x values here, plugging them in and seeing if we get answers. We plug a number into a calculation, we can't use it, we're not going to get an answer. So we want to just know the domain is what numbers can we use? And it's really helpful just to get a sign chart going here. Not a sign chart, but just a number line broken up into intervals based on critical values. What are the critical values? Making a 0 and using a 0. 0, critical. 4, critical. What are some of the operations we got to watch out for? Division. I don't think it's permissible to do that. I don't think you can divide by 0 in math. Doesn't make much sense. Even roots. I think even roots, like a square root, is important to know. That has to be greater than or equal to 0. So whatever's in here, I got to be careful. I got to make sure it's greater than or equal to 0. And logarithms have a parentheses where you input x values. You better make sure whatever's here is greater than 0. Very similar to the root. Roots can be 0, right? And we often solve equations with even roots, and we got to remember the plus minus. You also have to remember that you don't have a plus minus with odd roots. The cube root of -8 is -2. It's not plus or minus. Okay? -2 times -2 times -2 is -8. There's one answer. Whereas -2 times -2 is 4, and 2 times 2 is 4. Okay, so you got a concern there. So can I use numbers bigger than 4? 5. Square root of 5 divided by 5 minus 4. Do you think I'm going to get an answer there? I think so, yes. Let's try 4. 4 minus 4 is division by 0. No, not going to be able to use 4. Let's use numbers between 0 and 4. Let's put a 2 in here. Square root of 2 divided by -2. Will a calculator do that? Absolutely. You're supposed to know what that decimal is right now. -0.71. Okay. I hope you recognize root 2 over 2. All right, so yes, so this worked. Can I use the number 0? Square root of 0 is 0 divided by -4. So square root of 0 divided by -4 is 0 divided by -4, which is 0. I can use that number. Can I use numbers less than 0? -1. Square root of -1, oop. Imaginary, not going to show up in Rene Descartes. Well, it's not going to show up on that coordinate system, so no. That's an ugly looking no. That's a better looking no. 0. 4 doesn't work. Okay, so 0 works. 4 doesn't work, but everything past 4, I've got to have a parentheses again. Glad I got my eraser. To infinity. That's your domain for that problem. All right. So the argument of this problem is x cubed. And you have to recognize what x cubed represents. That's why we repeat these conversations. And I hope you can see that barely. I'll write it here. 8 sine, got that glare on the whiteboard. So what's the range? Well, now we're talking about y values. Y values, outputs, what comes out of this? Well, I think you have to understand that part. I don't think multiplication by 8 and addition of 5 is a problem. A lot of numbers come out when you multiply them by 8 and add 5. Question is, what is this creating? What is the sine function creating? That around the circle, around the circle, around the circle. We're drawing what? Triangles. And we're looking at that height divided by the hypotenuse of 1. I don't think the sine function ever gets bigger than 1 or smaller than -1. And I think that's just trying to throw you off. I'm not trying to throw anybody off. I'm trying to create conversations that you need to have. So what's x cubed represent? That's what it's representing. Angles. It's like putting angles here at x. At x equals -3. Well, what's -3 get you? -3 gets you -27. Now, -3 is right about there on the unit circle, going backwards, right? But what am I doing to this number? I'm cubing it. So you're really at -27. I don't know where that is. 6.28 is over here. So it looks like it's less than 5. Rotate 5 of these rotations. Well, actually, I'm going that way with positive. All right, so where's -27? Well, 4 gets me pretty close to 25. And I got to go another 2. I think I'm probably in this vicinity. But what have I done? I've gone 27. So there's 6.28 minus 6.28. I'm going pretty fast around the circle here. So what's this function going to look like? Sine of x cubed? If x cubed is my axis, well, when you think you're at 2 pi, you're really at 8 pi cubed. You're way down the line. I think initially you got a sine function that's slowly increasing, and then over time it's starting to 1, -1, 1, negative. But you don't have to worry about that, because the only thing you have to worry about is that this function only creates numbers between 1 and -1. So what's the biggest number I get out of this? 8 plus 5, 13. What's the smallest I get out of this? -3. There's your range. It's a conversation you have to have. You have to what? You have to broaden your horizons. All right, next. It's a review problem. So I expect that, I haven't put it on the board in a while. It doesn't feel like I have anyway, but this is all about Pythagoras. Where z, this is the z column over here, the constant, right? We're just trying to get a better sense of, hey, going around in circles with making those triangles. All right, so, but just shifting our origin from 0, 0 to someplace else. X minus 8 squared minus 64 plus y plus 2 squared minus 4 equals 2. X minus 8 squared plus y plus 2 squared equals 64, 68 minus 2 plus 2, 68 plus 270. All right, so what do we have? We have the square root of 70 is our radius. We now have a side length, that's x minus 8. We now have y plus 2. So where 0, 0, 0, 0 is now centered at 8, -2. And where's 8, -2? 8, -2 is over here. So my origin would be somewhere in this vicinity here above it. Okay, getting carried away here. Enough said. We've done enough of those problems. All right, so we're always looking for inverses so we can solve equations. So let's see. Get that glare. So I gave you f of x equals cosine x. What's the inverse? Maybe the notation now comes a little more important. The inverse of this is this notation was created to help us. Now, it'd be nice if you could tell me the inverse of what to what. Well, once again, you got to know what's in the parentheses. That's an angle. What do we get out when we do the cosine of 30 degrees? We get out a ratio. So therefore, what's the inverse of angle to ratio? I give you a ratio like the cosine of -1 of 1/2. Well, I hope you have that picture in your mind, 60 degrees. Put this in a calculator, you might see pi/3 pop out. There's more to discuss there. This is an entry level, think about it. And then that concept gets worked with and enlarged upon. We start to work with it, apply it to different problems. But we got to start the conversation somewhere. And where's the conversation starting? Language. What's in the parentheses to these commands? Angles. What do we get? Ratios. Good conversation to have. I lost my glasses. All right, so 73. I don't think I asked anything. So I'll have to amend these worksheets and ask a question there. Solving. Okay, well, it comes at you from left field. Okay, so how do we solve that? Well, the first thing I notice is everything's divisible by 3. I think I can make this smaller. I think I can look at x squared minus 4x equals 12. And I hope you either complete the square quickly, which I could do and get an answer here quickly, or ask yourself, can I factor it? Now, that's a really nice question. And I expect you can do that. I hope you can say x minus 6 times x plus 2 equals 0, and we get answers of 6, and we get answers of -2. That work in this equation. If I wanted to complete the square to get those answers, I could have. I could have said x minus 2 squared minus 4 equals 12. And then done what? Added 4, 16, taken the plus minus square root, and then added 2. 2 plus 4, 6, 2 minus 4, -2. There were different ways to do that problem. Would have done the quadratic formula, which would have been the least easiest way to do the problem. Okay, moving right along. Conjugate. And I hope you're in the habit of pausing the video. So I know 2 squared is 4 and 9. I know I'm going to get 13, so I'm going to take the shortcut. But you go ahead and multiply it out, see the middle terms drop. But you better get 13. I'm going to do this in my head. So that's positive 21i squared. So that's -21. 10 minus 21 is -11. And I've got -14, -15. I think I got -29i. And if I made a mistake there, somebody just write it in the columns, in the commentary, and I'll amend the answer. All right, so let's look at this and have a little conversation. Tell me if this is true or false. Pause the video, look at that. Tell me if it's true or false. And what patterns you see. Well, I see exponent 1. I see that exponent. exponents don't have much meaning unless you attach them to a base. I'm seeing that exponent is a 2. And I'm seeing 2 to the 1 plus 2 is the rule of exponents. And I think I'm highlighting 1 plus 2, but writing in a very strange way. And I also see a product here. 2 times 4, 8. Yeah, that's what you want to see, all right. You can multiply those products, those quantities. Oh, geez, I guess I can do that here. Let's make some space and do it. As a single logarithm, I think it's x squared minus 12x, base 2, base 4. Excuse me, base 4. I'm so used to doing the entry level problem with a 3. Well, early in the term, we looked at 5 to get 125 equals 3. Oh yes, 125 equals 5 to the 3. Oh, I think I can take that form, which is what form I have right now, and convert it to this. And sure looks like I'm finding the inverse of log base 5 is 5 to the. So I hope we've done this enough that you can see that this quantity is producing this quantity, which is 64. And 64 is 4 times 4 times 4, trying to get more familiar. And that right there is 16 times 4. And 16 times 4, ooh, they are 12 apart. So I'm going to make a minus sign there. I'm going to change that to 64. I'm going to set it to 0. And I'm going to write x minus 16 times x plus 4 is equal to 0. And I can see that I have 16 as an answer and negative 4. And from our earlier work, plugging in negative 4, that's a problem. Plugging in 16 isn't a problem. And 16 minus 12 is 4. And now I can see that what do I put on top of a 4 to get a 16? And if I add that to what I put on top of a 4 to get a 4, I think I've got a correct solution. All right, let's do this one quickly. Square root, square both sides. Okay, 2x minus 4 from a graphical standpoint. X minus 6 from a graphical standpoint. Looks like I've got a negative answer and it's not too big. X equals negative 2. That's what I see. Any domain restrictions? Yeah, this is a real problem. This is a big problem because I can't take square roots. Now I know why I asked this question. So let me do a little better graphical. All right. In fact, that's when I wrote this, I was thinking, I hope you know what these graphs look like. This one starts at 2 and is going up twice as fast as this graph. This one starts at 6 and isn't going up as quickly as this graph. I don't see a point of intersection. Now, when I first asked this question, I did not do it out mechanically. I looked at it that way. And that's why I wanted to ask it, right? To get you to visualize that solving equations is all about intersections of graphs. And if you can see those graphs in your mind's eye, you can save yourself a lot of work sometimes. All right. You know the drill for this one. We've been doing them enough in class that you should not have to ask me, what am I doing? You're trying to find ax squared plus bx plus c equals 0. Well, I don't see 0 on this side, but I can certainly get there. I can get there by moving things. So I'll move the 4. I want squaring, so I'll square both sides. I know 9i squared is negative 9. I'll bring it to the other side. And I'm done. And I expect you to be able to get these answers from completing the square, so let's get that practice in as well. I think that's enough. I think I'm showing you enough there to see where this is coming from. Let's move on. All right, the good thing about this test coming up is there's about 15 graphs. Maybe out of the 113 questions, there may be at least 10 graphs. And graphing should be 10 seconds or less. You should be able to sketch that at this stage. Done enough of them, you should be able to come right in here and look at the differentials. That's a 5. 6 to 29 is 23. I know my base is going to be 23 over 5. Okay, but let's write it. Y equals 6 plus 5, 23 over 5, 1990, x minus 1990, 1990 to 2025, 10, 35 years. I'm done. I want you to be able to do it that quickly. That students race. They get so good at this that they start racing me, saying, okay, let's take on the old guy. He's been doing it for how many years? Let's beat him. Gotta say, I'm happy. Hasn't happened yet, but it's come close. All right. Piecewise function. Pieces. All right, so I hope you're good at this now. I hope you know it's a V shape up. I hope you know that the vertex here is 7, 5. And I hope you know that on this side, if I follow from left to right, I'm going down. So that's minus 3, x minus 7 plus 5. And this side is going up. That's positive 3, x minus 7 plus 5. So Alfred Hitchcock becomes going down, x plus 7 minus 7 plus 5. But I'm only doing that because this hinges at 7. X minus 7 is a linear function that crosses the x-axis at 7. If I slap an absolute value, then all these negatives become positive. So it hinges at 7. So we want to show the reader that. So on the left side of 7, I'm decreasing. On the right side of 7, I'm increasing. And I got to put an equal sign one place or the other because 7 exists. So those are the pieces. You do it enough times, you're just writing your answer on an answer key. You've done the thinking, you've done the work. Now, I used to solve with the pieces, but it really is much easier solving for 23. So let's do that now. You can solve for 23 by pretending that these are parentheses. All right, but we will solve both values. We'll get both. There's all kinds of shortcuts here. All right, I'll do this one in my head, and we can find where 23 is right there. Okay, so 18, 6, 7, 13. 13 gets you 23. Okay, it didn't take long. All I did was pretend these were parentheses. Subtract 5, divide by 3, add 7. And now I know that I'm from 7 to 13, 6 units to the right. Therefore, 6 units to the left, 1 should work. 1 should get me 23. Okay. But let's go back to absolute value. Subtract 5, 18. Divide by 3, 6. Dropping the absolute value means considering the positive and negative values. But that's how much I'm changing from 7. Add 6, 13. Take away 6, 1. Right? Because the last stage is adding this 7 to that. All right. So once you find those numbers, we can see when we're bigger than 23, and it's not these x's in between 1 and 13 give me things smaller. So you already have your answer, but don't be afraid to make a sign chart. 13, 1, those were the values that equal 23. When am I going to be greater than or equal to 23? Okay, well, let's put a number in and find out. I know it's going to be true, false, true. Because they all three. But put a number in, like 1,000,000. Put 1,000,000 in here. Well, you can immediately see you're bigger than 23. True. And we have a linear function, so we're going to get sign changes. But you plug a 0 in. Real easy to plug that in. 21 plus 5. Where am I? Oh, 0. Yeah, that's true. I wanted to plug a number between 1 and 13. How about 10? 10 minus 7, 3, 9 plus 5. That's not bigger than 23. But 0 was. I would have preferred to look at that with negative a million. True. So what's your answer? Negative infinity to 1. And I also said equal to, so 1 works. Union 13 works to infinity. Okay, well, now we're getting down to the end here. Let me get rid of this. All right. Catch my breath. Move Rene Descartes down. All right, so this is just a little bit of a solving with a couple of variables. So let's pretend we have some value, some number, and we're multiplying by a, and we want to isolate x. All right, so what are the steps? I hope you can just write it on your answer key. You got to subtract 4. I'm going to get rid of these as we go. You got to divide by a, because that's multiplication. You got to know the inverse of ln. The inverse of ln is e to the. Yeah, you can see that. Multiplication, right? Division by 7. Multiplication by 7. Subtraction of 5. Addition of 5. Multiplication by 2 means this whole thing. This new number. Division by 2. And I hope you're training your brain to do that. Because then solving 90% of the equations you work with in math, they're like a metronome. Okay, so that's done. All right, let's get rid of that. Log base 9 of 1 over 27. Log base 9 of 1 over 27. Well, I guess that's asking the question 9 to the what equals 1 over 27. I hope you can do this conceptually now. I need a square root. I need to do what with the square root to get 27? I got to cube it, and I got to do what to 9 over 1? I got to reciprocate it. So I'm hoping you're at that stage. If not, then we got to do the mechanics. 9 is 3 squared. We need to get the same base, but we can't really compare exponents. That's 3 to the minus 3. So 2 times x equals minus 3, and my rotator cuff isn't going any higher. So I hope you can see minus 3 over 2. Almost done with these. Basically, a similar thought process here, right? I got to change 9 to 3 squared. Now I've got the rules of exponents. So x equals 2 times 2 things. 2 things. I got to double both. 4x minus 8. Okay, so I can see 3x is equal. Bringing them that way. So let's do it this way. I can bring the 8 this way, that way, and I can see 8/3. So I got to get a number. The number, well, enough said. I was going to talk about cube rooting, 8th powering, but it's all right. This should be memorized at this age. So that's 10x plus 5y. And then the next parentheses gets built off of that. And on the YouTube channel, there's factoring the sum and difference of 2 cubes. It's explained. I'm not going to do that now because we've been doing so many of them. So we got 100x squared. That product is 50xy. You got to get rid of that. And you got to square that. 25y squared. I'm not going to explain that. We've done too many. 4th root 32 is 2 to the 16. Okay, so I know the 4th root of 16. I know the 4th root of 16 is 2. But that 2 stays inside. The 4th root of x to the 4. 4 goes into 4 once. I'll write the 1. Y cubed? Not enough there to take 4th root of cube. 3 dimensions, I'm looking for 4. 23 though, 4 goes into 23 5 times. Yeah, z to the 5th times z to the 5th times z to the 5th times z to the 5th is z to the 20th. I need another 3. I need 1 more to get to 6. Done with that. The last problem. The ln of e to the 3 over e to the 7 cubed. I'm going to go back to day one in this class. Hang on, got something over here I want to look at. Pertains to this problem. And I'm hoping the conversation we're going to have helps you understand this at a little deeper level. So let's go back here, Renee. Folks, remember the very first day? Very first thing we looked at was this sentence. And I said, if we're going to do mathematics, we better find a better way to communicate, because that took me a long time to write. And so how do we communicate math? Symbols. So you write down what I'm putting in front of you and see if it makes, if there's a big difference between when you first saw this sentence and how you read it now. I hope there's a major difference. The value of the exponent that you put on top of a 5 to get 25 is a 2. When I ask Algebra 1, Algebra 2 students to write to me what I've written, every single year somebody says 5 squared equals 25, and that's logical. It's logical, it's true that 5 squared is 25, but that's not what I wrote. What I wrote was, from left to right, the value of the exponent. That's what this command is all about. Exponents, values of exponents that you put on top of a base. And in this case, the base is a 5. That you put on top of a 5, right there, triangle, a rectangle. To get, parentheses, to get 25 underlined may be written as equals A2 star. So when you see a logarithm, you're looking for the value of an exponent on top of a base. Let's go back to this problem now. See if it has a lot more meaning. And let me highlight it up here so I can write it more easily. Okay, I think that's what I got. I think it was -3 on your sheet. I think it was -3. So let's go with this. Okay, so the first thing I see is a command, ln. Well, that's called the natural log, but it's still a logarithm. And it's such an important one, we don't write the base, but it's base E. Well, I got a lot of exponential activity, base E activity here. Can we simplify it? Absolutely. E to the 3 over e to the 7 is e to the -4. Maybe it was a 3. I don't know. Maybe it was a 3. If it was +3, then your answer is -12. If it's -3, then it's +12. But that is the exponential activity, base E. Okay, that was my attempt to hopefully make that understandable, or at least more easily understood. All right, so more problems, and you want to get to the point where a lot of these problems are like a flashcard, where you go 3 times 5 is 15. You don't have to think about it, and that's what we're hoping. You see a quadratic, you set it to 0, you try to factor it, you do it immediately, so on and so forth. Points of inflection of a cubic, minus b over 3a pops into your head, you do it quickly, so on and so forth. All right, and the only way that happens is if you're going to remember something, it's got to be important. You have to attach some importance to it. And if you hope to move up the ladder in mathematics, it's important. All right, toodaloo, enjoy your day.